Hello everyone and welcome to our Physics 2 lab project, Geometric Optics, Reflection and Refraction. My name is Michaela Lohr. Our objectives in this lab are to demonstrate and apply the laws of reflection and refraction through ray tracings, cylindrical mirrors, a prism, and light sources, and to understand optical phenomena such as rainbows and total internal reflection. Here's an example of reflection in nature and refraction through a prism. Calculating reflection, we see that we have two different types of mirrors, a concave mirror and a convex mirror. In a concave mirror, we see that we have a real focal point, meaning there's a positive focal length because the rays are directed and converge at a point that is in towards from the mirror. The focal length is directly related to the radius of curvature, and the equation we use here is F equals R over 2, F being the focal point and R being the radius. In the convex mirror, the virtual rays converge to the focal point behind the mirror and is therefore given a negative focal length. The focal length is inversely related to the radius of curvature, so we use F equals R over 2, but the negative form. In calculating refraction, we use Snell's law, n1 sine theta 1 equals n2 sine theta 2, meaning there is a direct correlation between incident ray and refracted ray and their indices of refraction. We also see that total internal reflection can occur when the critical angle is passed, and the critical angle is the point where there will be a 90-degree angle in the second medium, and this happens if refraction is from a high refractive index to a low refractive index, then the angle of refraction will always be greater than the angle of incidence. And total internal reflection can never occur when light travels from a lower refractive index medium to a higher refractive index medium, because there is always a path for the light to refract into a higher refractive index medium. We also see that when you use a glass prism and shine a beam of white light through, we should be able to see a spectrum because each of the different colors has different indices of refraction. The purpose of this lab is to explore the principles of reflection and refraction through practical experiments with mirrors and a prism.
Hi, my name is Lillian Adams, and I'll be talking about our methods and results. These are the apparatuses that we used when conducting our experiment. So in activity 1, we were looking at reflection using mirrors. We used a flat mirror, a concave mirror, and a convex mirror. We first used the flat mirror and positioned it directly in front of the light source, and we traced the rays and the shined rays and the reflected rays on a piece of paper. We did that for each one of the mirrors. And obviously with the flat mirror, the reflected rays went straight back onto the shined rays. For the concave mirror, we placed it in front of the shined rays and we traced where the reflected rays converged at a single point. We traced that onto the paper. This singular point is known as the focal point. We then were able to use a ruler to measure the distance between the focal point and the mirror, and this gave us the focal length, which we would trace on our paper, and I'll show you in a second. For the convex mirror, we repeated the same steps, and since the reflected rays diverge, we know that the focal point is there for virtual because it is behind the mirror and is also considered negative. So we drew the diverged rays, and then we were able to do the same calculation to find the focal point and the focal length. So here you can see for our drawings for the flat mirror, For the concave, you can see there's a focal point, and the focal length we got was 58 millimeters. And then we used the radius, we calculated the radius using the curvature of the mirror to deduct what the expected focal length would be. And then we did the same for the convex, noting that it's negative because it is behind the point of reflection. In activity 2, we were looking at refraction. Through a prism. We used a trapezoidal prism and shined a single light ray through it and traced both the entry and exit points. Using this tracing, we were able to calculate the angle of incidence and the refraction to confirm Snell's law, and also the prism's index of refraction, which is 1.49. Then we gradually rotated the prism until no refraction occurred at the second boundary, which indicated the critical angle, as talked about earlier. We measured this angle to use it along with previously calculated index of refraction. Lastly, we looked at dispersion and refraction for different colors. We shined a single light source through a triangular prism to separate it to the component colors, red, blue, and yellow. We traced these on a piece of paper to calculate their angles. These are our tracings for using the prism, the first prism. And this is our tracing using a triangular prism, and you can see the angles for red, yellow, and blue. And here are our results. For the concave mirror, our percent error was 0. For the convex mirror, our percent error was 1.7%. For Snell's law, our percent difference for N1 was 2%, and our percent difference for N2 was 2% as well. Our percent difference for total internal reflection was 0.47%. And here you can see the index of refractions. They decrease as the colors decrease on the spectrum.
Hi, my name is Logan Johnson. So from our conclusion, we found that F does equal R over 2, and we found this with very high precision and accuracy. We also found that if refraction is from a high refractive index to a low refractive index, then the angle of refraction is always greater than the angle of incidence. We also found that total internal reflection can never occur when light travels from a lower refractive index medium to a higher refractive index medium. This is true because there is always a path for the light to refract into the higher refractive index medium. In other words, if you were to be underwater looking up and you could create a situation where all of the light reflects off of the surface of the water, but if you were to be above, you could not create that situation because you're going from a refractive index of lower N to higher N. Our above and beyond has to do with invisibility cloaks, which utilize careful engineered materials to bend light around an object, making it unseen to the human eye. This has a lot of applications with military or even scientific studies in order to better understand how we can create these invisibility situations. Thank you guys so much for listening to this presentation. And we'd like to especially thank Dr. Vola for his help with this lab, and we'd also like to thank Oscar Corral's Mazda, which unfortunately did not see a good ending to this semester. Thank you.